Rigidity. It's the name of the game in machining setups. A lot of different tools can help make sure your part doesn't deflect under load, and one of the most common supports is a machinist jack. Now machinist jacks come in all shapes and sizes, but their precision usually leaves a lot to be desired. They're typically simple, quick designs intended to just get the job done. And while there's nothing wrong with that even in the slightest, I seem to be fundamentally incapable of making either simple or quick projects. In this case, I'm looking to make a more precise and easier to use alternative to the traditional designs. So that's exactly what I'm going to make. A better machinist jack. Before I get started, I need to give credit where credit is due. The initial concept of this design comes from Mr. Art McKay of Washington State. What started as a discussion in the comments section soon evolved into a lengthy back and forth over email as we bounced ideas around. It's a pretty clever but still fairly simple concept that should solve a lot of the problems with typical machinist jacks. And if I remember correctly, he's not yet attempted this design himself. So thank you, Art. Let's see if I can do it justice. Now these problems with traditional machinist jacks, what are they? Well, the biggest one is that typical jamb nut designs like this have a tendency to lift out of position as the nut is tightened, which can be a real pain when you're trying to support material accurately. Secondly, there always seems to be a compromise on the thread pitch selected. Fine threads are good for precision, but take an eternity to adjust into position. And coarse threads are good for speed, but not as precise. But Art's idea combines the best of both worlds. A couple other wish list items for this build are 1. They must be short enough to match my vise height, since this is probably the most common use for these jacks. And 2. They need to be mountable with the mill's T-slot hardware. With a set of requirements and a few basic measurements in hand, it's time to start machining. Ha, just kidding. You didn't think I would just jump right into making chips, did you? There's way too much going on here for me to just be winging it. I'll spare you the part where I erratically sketched out different geometries while I roughed out the dimensions, and bring you along for the final design. The jack will be a 3-piece mechanism, and I'll start with the top piece, which I'll call the anvil. The anvil is what engages with whatever material the jack is supporting and will have just a simple round face. I'll add knurling to this bit to make it adjustable by hand, but I'm also going to add a couple wrench flats just so I can make adjustments that way if I need to. The shaft is threaded, and while a 1/2 inch 20 fine thread would work here, I'm taking it to the next level and making this a 1/2 40 thread. This will allow for the superfine adjustments I'm looking for in this build. The next piece of the jack mechanism is what I'm calling the sleeve. The top end of the sleeve will have a knurled knob, and there's a matching 1/2 40 fine thread to the anvil shaft on the inside. The outside is also threaded, but at a much coarser pitch. Actually, I'm going to use the coarsest pitch available on my lathe of 4 threads per inch. The only issue with this is that the thread height is just too deep for this part. So to get around this, I'm going to cut what's called a multi-start thread, meaning there will be multiple sets of threads running parallel to one another around the outside. This in effect lets me maintain the 4 TPI pitch while having a much lower profile. How I'll machine this should also be pretty interesting, so I'm looking forward to giving that a try. Now if you thought this part couldn't get any cooler, let me tell you, we're just getting to the good stuff. The top end of the sleeve with the knurled grip will actually form an integrated locking collar. This is one of the core design elements that comes from Art and should have a couple huge advantages. Number 1, the tooling required to make the adjustments is minimal, just an Allen wrench. And 2, when the locking collar is tightened, in theory the anvil height should stay exactly the same without lifting as would happen with a jamb nut design, making it far easier for setting precise heights. The final piece of the puzzle is the base. This will have a combination of knurled grip sections on the top and bottom, as well as a set of wrench flats in the middle in case they're needed. The unique locking collar design is used once again on the top side where the sleeve will be inserted, and most of the length of the internal bore will get a matching multi-start thread to the sleeve OD. The last bit will be a 1/2 13 threaded hole in the bottom, making it compatible with my mill's T-slot hardware. And then that's it. That's the whole design, and I think it's actually going to work. I'll finish dropping all the dimensions on here and we can get to making. Of course, like most projects, order of operations is going to be critical here. So I'll start with the part I have the least control over, but also the most risk of screwing up, the sleeve. Also, I'll be making these parts from some A2 tool steel slugs that were donated to the channel by another very generous viewer. Knurling is somewhat of a black art, so anytime I have a part that includes this, I always try to knock this out first, just in case it doesn't go as planned. I'll face the end of the stock, then turn down the OD to my starting diameter. After ensuring the knurling tool is going to produce the pattern I'm after, I'll proceed across the rest of the area until I have a nice grippy knurl. The challenging part will be to get the rest of the knurled parts to match, but I'll cross that bridge when I get to it. Next, I'll turn down the end section that will make up the external threads, and also clear a little starting spot near the knob for the thread cutting tool. Now you might recall from before that these threads will be multi-start threads, and there are a couple ways to do this. If I were cutting double or quadruple start threads, there are some specific scenarios where I can make clever use of the threading dial, but I won't be getting into that since I'm making triple start threads. To achieve this, I have to set the compound rest to exactly 0 degrees. This in effect gives me an additional z-axis which I can then use to set the thread lead, or rather the distance between the 3 separate pitches. The only downside of this is that I'll have to feed the thread cutter in straight rather than at 60 degrees, which is my preferred method and it usually results in a better finish. But we'll see how it goes. I'll also point out that I'm cutting these threads in reverse with an inverted thread cutting tool, which will greatly reduce my risk of crashing into the part. I'll set the lead on the compound to 0, coat the part in some layout fluid and take the first scratch pass. And here you can see just how coarse of a pitch this really is. I'll adjust the lead to 1/3 of the pitch, so 0.0833 inches, and take the second pass. And finally adjust the lead one last time to 0.1667 and take the final scratch pass. I'd say that looks about right, so I'm going to go ahead and start making the real cuts. I know roughly how deep I need to go, but rather than just adjust the lead between each pass, I'll do this one thread course at a time and only adjust the lead between the courses. Of all the things that have to go exactly right, the adjustment of the lead is the one I have the least precision over. Since there's no DRO on this axis, I'm limited to the accuracy of the hand wheel, which only shows increments down to the 1,000th. But I'm still trying my best to aim in the neighborhood of a couple 10,000ths by splitting the increments. It might be wishful thinking, but I at least have to try. Since I don't have a matching female threaded piece to check the fit on, I'll have to resort to using thread wires. Placing 2 on the threads on one side and 1 on the opposite side, I can get a reading with a micrometer. Then compare this with the results of an online thread wire calculator, taking into account the wire diameter and the thread spec. This is technically a 7/8 by 4 thread, but since this is a triple start, I'll use the values for a 7/8 12 instead. And find that I still have a fair amount to go. It wasn't until these deeper passes that I started getting some rather crunchy sounding cuts. This is likely due to feeding the cutter straight in and also running a bit slower for the diameter, both of which I'm limited on. The one thing I definitely had control over, however, was just how far out the cutting tool was sticking from the tool holder. Why on earth I didn't reel that in a bit before getting started is beyond me. So to try and smooth out the final finish, I'll take 3 to 4 spring passes on each of the thread courses. And also use a triangular file to remove any errant burrs before measuring. That looks pretty good. Once at the correct thread dimension, I can move on to the bore. I'll pilot drill for a 1/2-40 tap, and also use the boring bar to cut the bottom clearance hole for the T-slot hardware that will protrude into this area. It wasn't until I had this 1/2-40 tap in hand that I realized just how fine thread this actually is. Here's a common 1/2-13 for reference. Bananas. I'll get this set up with a guided T-handle tap wrench, then start the many revolutions to get it all the way to the bottom of the bore. Turning both the inside and outside threads in the same setup like this ensures that all the adjustment axes remain parallel, which will be key for getting the precision I'm hoping for from this jack. With the fine threads tapped, the last feature I can take care of from this side is the bottom chamfer of the knob. Then I can part this off. Nice catch. In addition to cleaning up the opposite face, I still need to add the features that will turn this knurled knob into a locking collar, but I have a little trick up my sleeve for these that I'm not quite ready to reveal. So in the meantime, I'll get started on the anvil. Again, I'll start the same way as before by facing and turning down the diameter in preparation for the knurling. And then cross my fingers that the pattern comes out the same as the sleeve. 2 out of 3. This must be my lucky day. With the tricky part sorted, I can begin turning down the rest of the shaft in preparation for the 40 TPI threads to match the bore of the sleeve. But not without a little side project first. While most of this lathe's thread feeds can be achieved with correct lever selection, a 40 TPI thread is not one of them. So I'm going to have to make a change. To the change gears, that is. I currently have the A set of gears installed, but I need to swap to the B set of gears, which are conveniently located at the bottom of this awkward and nearly falling apart crate on the lowest shelf on the back of my workbench. I think I should at least get a point for keeping all the lathe miscellanea in one spot. I'll get these cleaned up real quick, then loosen the change gear mechanisms behind the cover to make the swap. This change requires 3 out of the 4 gears be replaced, and because the different gear sets have different diameters, there's built-in flexibility to allow for the gears to properly mesh in each configuration. With everything tightened down and the correct selections made on the front of the lathe, I can take my first scratch pass to ensure I got everything installed correctly. Looks like I did, so it's time for the real thing. Since this is such a fine pitched thread, I won't be cutting very deep. But I am keeping the passes to a couple thou at a time just to reduce the deflection of this 3-to-1 stick-out ratio. Once I start to get close, I can use the internal thread from the sleeve as a gauge until the threads just barely fit. Keeping the play between the threads as low as possible will be another factor in making this jack super precise. Then that's it from this end. Like the sleeve, I still have some work to do on the opposite end, but again I'm going to put that on hold. I know, 2 unfinished parts. But bear with me because it's going to be awesome. I'll swap the change gears back to the original set and then get started on the final part of this trio, the base. Again, I'll face and turn this in preparation for knurling, but this time I'm also bringing in some tailstock support since I need to knurl all the way out on the end. I somehow missed filming this, but my first test of the knurling tool was producing the wrong pattern. So I ended up turning another 5 thou off the diameter, which helped in getting the knurling to match the other 2 parts. To cut the narrow center section, I'll zero a neutral angle cutter on the end of the stock with the old micrometer, and then hog the material away in the middle. I'll also drop a chamfer on this end as well. Then change gears again and work on the bore. Well, not the change gears, you know what I mean. The threads at the back of this hole will be a half 13, so I'll first pilot drill deep enough to clear what will be the bottom of the jack, then switch to a much larger diameter drill to start the shorter pilot hole for the internal multi-start threads. I ended up using another online tab calculator to determine the ideal pilot hole diameter for this custom thread. So to take it the rest of the way, I'll use the boring bar. And then switch to the threading bar to clear the thread starting area at the bottom of this hole. Not the preferred tool for this, but it gets the job done. While I've taken up the practice of threading in reverse for external threads, I haven't been properly equipped to do this for internal threads. That is, until now. Knowing I would be taking a ton of passes inside a blind bore, I decided to treat myself, and bought a left-handed threading insert bar. While simply flipping a right-handed threading bar works for cutting external threads in reverse, the only way to do this for internal threads is with a left-handed tool like this. I'll get the thread feed and compound dial set up just like I did before on the external multi-start threads, then begin taking passes on each of the thread courses in sequence. This time using the external threads of the sleeve I made as my gauge on how far I need to go. Like before, as it starts to feel like it's going to go, I reduce my passes to a couple thousandths at a time, and also take many spring passes, until all of a sudden the sleeve fits. This is a great sign considering all the things that could have gone wrong with aligning the multiple pitches. But I'm not super happy with the fit of the threads. Sure, they're smooth, but they're also way looser than I was hoping for. I'm a little uneasy that this might affect my precision in the end, but I think I'll keep trucking along on this one, work out any bugs that might crop up, and remake this part later on. The next set of operations on the base require some milling, but rather than de-chucking the part, I'm going to de-chuck the lathe entirely. I'll mount this whole thing on the rotary table with the chuck adapter I made a while back, which already happens to be trammed to the mill from my last project. So the only indicating needed is to zero the DRO on the part. How convenient. Now I can begin cutting the features for the integrated locking collar. I'll start by milling the tangential counterbore for the locking screw. Then switch to the drill chuck and drill the through pilot hole for the 1032 tap, and also the screw clearance hole in what will be the top half of the collar. After tapping the hole and giving a test fit with a screw, I can swap to the slitting saw and cut the slit that makes this locking collar actually lockable. Note the direction that I'm cutting into the threads. This prevents burrs from forming on the inside of the thread, which would be a real joy to remove. Alright, with the slot cut, we can actually see if this is all going to work. While it does take a fair amount of gronking on the locking screw, it does eventually tighten down on the sleeve just like I hoped. I imagine this will be even better with a closer thread fit. At this point, you might have picked up on my clever plan to finish the final two parts. One of the biggest advantages of this rotary chuck adapter is that I can switch back and forth between the mill and the lathe without removing the parts from the chuck, and thus losing my reference axis. Pretty neat, right? With the chuck mounted back on the lathe, and the sleeve clamped tightly in the base, I can put the final touches on the unfinished end of the sleeve. It was at this point I noticed there's a quite concerning wobble in the setup. The exact opposite of the intent of this approach. I narrowed down the wobble to the deflection of the locking collar due to the oversized internal threads. I should probably hold off on machining the rest of these parts until I can remake this base, but I'm going to go ahead and proceed with the rest anyway. I'm a little impatient to see the whole jack assembled, and I can always refinish the end slightly out of spec later. I'll pop this whole setup back over on the rotary table, counterbore drill and tap the locking collar screw hole in the sleeve, and again cut the slit with the slitting saw. This time around testing with the anvil inserted, it takes significantly less torque on the screw to lock the anvil in place. No surprise as this thread has a much closer fit. However, it reaffirms the importance of fixing the fit on the multi-start threads of the base. But again, I'll keep going. With this still mounted in the mill, I'll go ahead and cut the wrench flats on the anvil, as well as the flats on the base. Then I can throw this back on the lathe one last time, where I can put the final touches on the anvil face. Barring the slight wobble I had from before, I think the advantage of never breaking down the base setup from the chuck is pretty awesome. At all points through the machining, I'm able to maintain concentricity through each of the parts and in the assembly as a whole. That is, until I part the base off for good. This leaves one last face to clean up with no obvious way to grab it and ensure that the bottom will be square to the jack's center axis. But after some head scratching, I think I've got something that'll work. First, I'll lightly grip this by the knurling, just enough to tap the base for the 1/2-13 T-slot hardware. Then I can actually thread one of the studs into the base like so, grip that in the chuck of the lathe, and tighten the face against the chuck jaws. This should guarantee that the base is machined parallel to the opposite face, which we already know is square to the center axis. Then I can face the end square into length, and add the last and final features, which are of course the chamfers. And that's one jack complete. While this would certainly function just fine as a basic machinist jack, it's still lacking the precision I came here for in the first place. So now that I have all my setups figured out, I can remake the base one final time. Well, that didn't work. I overshot the threads, again. I cut them a full 10 thou smaller than the first time, but this feels just as loose as before. While I was cutting though, I think I observed the problem. With the cutter height set exactly on center line, the forces are pushing the bar down and causing the threads to cut a little bit deeper than I intend. This may be a long shot, but I'm going to try again, but with the cutter height set about 20 thou above center line. And that's more like it. It's right at the verge of being too snug to turn freely, which is exactly where I want this to be. Perfect. I'll do the final touches on the mill, then it's back to the lathe to reface the sleeve and anvil to bring them square to the base. After finishing the opposite side, that's one precision jack complete, and man does it look slick. The true test of precision, however, is still to be revealed. I'll get this anchored to one of the mill's T-slots, then bring over the surface gauge with a 10,000ths indicator. The triple start 4 TPI thread on the sleeve eats up the bulk of the distance, then switching to the fine thread of the anvil and the resolution is phenomenal. I can easily set this within a 10,000th of an inch. And then, when I lock the collar, absolutely no movement off of its setting. This is amazing. I'm so pleased with how this turned out. Wait, dude, what did you do? You were done. Well, long story short, I was attempting to correct some slight squareness problems I was seeing. The head of the anvil was reading about 3 thou variation across the surface, which I knew I could fix with the surface grinder. I ground the base successfully, but then when I was going to set up the anvil in place, the silliest thing happened. My brain confused my left hand for my right, and more catastrophically, my right hand for my left, driving the grinding wheel down into my machinist jack way too hard, which instantly sent my glorious jack flying off the chuck, taking a not so small piece of the grinding wheel with it. and also leaving some other carnage in its wake. So now we're here, with an awesome but battered machinist jack. I've run out of time to remake the whole anvil, so to at least make this functional again, I'll turn a steep taper on the face to clear the damage, and also reduce the contact area to a small narrow spot in the center. Not ideal, but it will tide me over until I can make this jack's counterpart and remake the anvil correctly. Other than that little hiccup at the end, I think this project has had a very successful outcome. I got to try out some of my shop-made tools, as well as a few techniques, which is always fun. But more importantly, I was able to prove out a brand new concept for a machinist jack thanks to Art and his great idea. And I might even venture to say this could be a real game changer. As always, thanks for watching, and see you next time.